In this video, we're going to define and explain the P-box in cryptography. We'll talk about its properties and implement it in code. Then we'll look at the P-boxes used in the data encryption standard DES. And finally, we'll test out our code by implementing the initial permutation of DES. Alright, the topic of this video is the P-box in cryptography. The things we're going to be talking about are the definition and the basic properties of what a P-box is. Then we'll look at the P-boxes that are used in the data encryption standard DES, just to see some real-world examples of how the P-boxes are used in actual encryption algorithms. And then we'll implement a general P-box in code. So maybe the best place to start with to develop an intuition of what a P-box is to look at how a P-box is in hardware. And this will give us a good guide of an intuition of how the mathematical definition should be later on. Although I think hardware is extremely interesting and very cool, I don't actually know anything about it, so I'm going to have to BS my way through this part of the talk a little bit. So let's imagine that we have 5 electrical sensors, whatever that means. And let's say we have 5 wires that are leading to these electrical sensors, and each wire is independent. So electricity can flow through each wire or not. The way we interpret this is that if there's an electricity flowing through a wire, then there's going to be a 1 recorded at the electrical sensor. And if there's no electricity in the wire, then it's a 0. And since each wire is independent and electricity can be flowing through each wire or not, that means we can represent any sequence of 5 zeros and 1s using this technique. We just choose to make electricity go through the wire or not, depending if we want a 1 or a 0 there. And now let's say we have another set of sensors. Let's say we have 7 of them here. And we want to wire the input sensors to these output sensors. And the main rule is that every output sensor needs a wire connected to it. We can't leave any of these output sensors without a wire connected to it. And just to make it clear that you're allowed to branch off input sensor wires to more than one output sensor. That's allowed. And you're also allowed to not use an input sensor if you want. You could leave a wire to an input sensor and then not wire it up to an output sensor. So let me explain what I mean by that. Let's say we take our blue wire here and we decide to hook it up to this particular output sensor. And that means if there's a 1, in other words, if there's electricity flowing through that wire on that first position, that electricity is going to carry through that wire and also give a 1 at this input, at this output node here. And let's do the same for the red wire. There we go. But remember, we're allowed to branch off. So let's say we extend the red wire to go to 2 different output nodes. That's allowed. And similarly, let's take the green wire and let's extend it down to this first output sensor and maybe the second and the last one as well. That's allowed. We're branching off to 3 different output sensors from 1 input sensor. That's fine. And then finally, just let's take this orange wire and extend it to this second last sensor here. And there's a complete wiring up of a P-box in hardware. That's what a P-box looks like in hardware. Notice the purple wire there. It didn't get wired up to any output sensor, and that's okay. So that's allowed. And often a P-box in hardware, it's called a cross wiring, and you can see why, because we're just wiring one set of input sensors to another set of output sensors. And since the amount of time it takes to go, electricity is flowing at the speed of light, so the amount of time it takes to go from the input sensor to the output sensor, although it's not 0, it's extremely, extremely small. So a P-box essentially takes no time in hardware when it's implemented. All right, so that will be a guide for our intuition of what a P-box is. Let's try to abstract that a little bit now. And let's just draw it as an arrow diagram. So we have basically 5 input sensors, or 5 input bits, let's just say. And we need to map these bits to 7 output bits. And when we just use arrows to indicate how the mapping should go. So no matter each of these B values, B1 up to B5, can be either 0 or 1. And whatever those values of 0 and 1 are, they get carried through to the output values to form an output value for any input value. So just remember, the main thing when you draw these arrow diagrams is that every output bit can only have should have one and only one arrow coming into it. So just to see some examples of things we're not allowed to do when doing an arrow diagram for a P-box is that you can't leave any output node unassigned by an arrow. That's what this first picture is showing here. We have that one output node that doesn't have an arrow to it. That's not allowed. Every output bit needs to be assigned. And similarly, over on the second picture here, we have 2 arrows coming into a single output node, output bit. That's not allowed either. So we can only have 1 arrow going into each. Otherwise, we don't know which bit to take to assign to the output. And just to emphasize some things we are allowed to do is we are allowed to leave off some of the input bits. So in this first picture here, B4 doesn't have an arrow coming out of it. It's not being used in the output, and that's okay. Although we are losing the information that's present in B4, whether it be a 0 or 1, if we leave it unassigned, then it'll just die there. That information will be lost at that point. And similarly, in this other little diagram here, it indicates that if we have one input node like B2, you can branch off to several different output nodes. Of course, it's going to be the same bit value on each branch, but you are allowed to duplicate an input value to multiple output values. Now let's get a little more mathematical here and introduce some notation. Let's say Bn is just a set of sequences of n bits. So each B1 up to Bn are just the value of 0 or 1. And we look at those as n tuples. And we interpret here Bn to be the least significant bit. And the most significant bit will be the first non-zero bit on the left. So that means there'll be a unique index k for which bk is 1. And every value of bi before that will be 0. So namely, bi will be 0 from 1 up to k minus 1. And it's important to realize that these sequences of n bits can be thought of as the integers from 0 up to 2 to the n minus 1. And a bijection from that is just taking the n tuple b1 up to bn to be the summation of the powers of 2 with those bi's as the coefficients. That's just a binary expansion of integers, right? And so for this reason, we call the elements of Bn as n-bit integers, okay? All right, so using the notation Bn that we just introduced, we can write the P-box in a function notation style, and it'll look like this. P will go from B5 to B7 on this last example. And what does P do to a typical element of B5? Well, P evaluated at B1 up to B5 is this quantity here, B3, B3, B2, B2, B1, B5, B3. One thing we notice here is we can represent this a little bit more concisely by just looking at the indices of the output value. In this case, it's 3322153. We don't really need to specify all that other stuff. And we can do this in general. So in general, a P-box from Bn to Bm can be just described as a list of positive integers, P1 up to Pm. The length of the list has to be m, which is the number of output bits. And each integer in the list is a positive integer lying between 1 and n being the number of input bits. So just to see some examples of that, let's say we take m to be 4 and m to be 6. So a P-box from B4 to B6, how would that look? Well, it'll be a list of 6 integers, and each integer needs to lie between 1 and 4. And for example, 2, 4, 1, 3, 1, 2, that would represent a map, which is a P-box from B4 to B6. And then another example here, let's say n is 6 and m is 4. So a p box from b6 to b4 would be described as a list of 4 integers, and each integer there must be between 1 and 6. So for example, 4, 1, 5, 2. Let's just say we have a list of m integers, p1 up to pm, where each of these pi's are from 1 to n. We see that that's just another way of expressing that we have a function, sigma, let's call it, from the segment of integers from 1 up to m to the segment of integers from 1 up to n. And what is this function sigma I'm talking about? Well, sigma I is just the value of p of I, the ith element of the list. It's just a simple change of notation in language, but it's a little bit nice to phrase it that way, because then we see that any p box from bn to bm is really associated or coming from a function, sigma, from the segment 1 up to m to the segment 1 up to n. And this really leads to the mathematical definition of a p box. And here it is. Let's just say we have any two positive integers n and m, and we take a function sigma from the segment 1 up to m to the segment 1 up to n, and let that be any function. And the idea is that using that function sigma, we can define a p box from bn to bm. And what does p sigma do to a typical element of bn? Well, p sigma sends x1 up to xn to x sub sigma of 1 up to x sub sigma of m. So it basically takes the n input values and it applies the sigma function to the indices, and that causes a shuffling of the indices. Now, we might have left off some indices, we might have duplicated some indices, but regardless, we're using the input value bits, x1 up to xn, and we're shuffling them somehow to get an arrangement of output bits. And this is what we call a p box, and sigma is called the associated permutation function of the p box. And we usually just write p instead of p sigma. But realize that any p box really has an associated permutation function sigma associated to it. Now, usually when we write this, the function sigma, we just specify it by giving it as a list of its outputs like we talked about before. So really, when we talk about a p box in practice, we're just giving a list of its m output values of its permutation function. One thing we can see right away from this definition is that if we define 0n to be kind of like the zero vector of bn, so all the bit values are 0, and if we define 1n to be the vector of bn, which consists all of 1s, then no matter what p box we have, p from bn to bm, p is always going to send 0n to 0m, and p will always send 1n to 1m. So if your input has all zeros, and you put that into a p box, necessarily the output will all be zeros as well. And if your input to a p box is all ones, then your output will all be all ones as well. Maybe the intuition behind that would be is if none of the wires have electricity in it, the output nodes, none of them will have electricity either, right? So 0 goes to 0. And if all of the wires have electricity in it, then the output nodes or sensors will also be, everyone will have electricity in it as well. Now, how about this? When is a p box 1-to-1 and when is it onto? Well, just remember some basic results of set theory. If we have two finite sets, x and y, and we have a function f between them, f goes from x to y, then we have some basic results here. For f to be 1-to-1, we need that the initial set x to have less than or equal cardinality than the final set y. And for f to be onto, it's opposite. The initial set x has to have a cardinality greater than or equal to the final set y. And if f is a bijection with finite sets, we need those cardinalities to be the same, whatever that may be. But they have to have the same cardinality if we want any hope for f to be 1-to-1 and onto, which is the definition of a bijection, right? And let's say that we have the cardinality of x being equal to the cardinality of y. Then it's actually equivalent that f is a bijection is equivalent to f being onto, and that's equivalent to f being 1-to-1. Those are all if and only if statements there. So if you know the cardinality of x is equal to the cardinality of y, and for some reason you know your function is 1-to-1, then necessarily it's onto, and hence it's also a bijection. Now, in our case, the sets we're working with are Bn. And the cardinality of Bn is obviously 2 to the n. We have n positions. Each one could be an either a 0 or a 1. So we have 2 to the n elements of Bn. And so talking about the cardinality of b to the n being less than or equal to the cardinality of b to the m is just the same as saying 2 to the n is less than or equal to 2 to the m, which is obviously just the same thing as saying n is less than or equal to m. So for a p box, let's say we have a p box p going from bn to bm. For p to be 1-to-1, it better be the case that n be less than or equal to m. It's not a guarantee, but it's necessary. If we want p to be onto, we need that n be greater than or equal to m. And for p to be a bijection, n better be equal to m. And if n is equal to m, then the conditions that p be a bijection, p being 1-to-1, and p being onto are all equivalent. So if you have one, necessarily you'll have the other two. Now in general though, we can express whether p is 1-to-1 or onto or a bijection in terms of the permutation function sigma. So let's say we have a p box from bn to bm and the associated permutation function sigma from 1 up to m to 1 up to n. Then p is 1-to-1 if and only if sigma is onto, right? The opposite property. P is onto if and only if sigma is 1-to-1, and hence it follows that p is a bijection if and only if sigma is a bijection. So those are very easy things to prove. And if we apply these ideas when a p box is presented as a list to us, then we can make the following statements. If we ever see any of the numbers from 1 up to n that are missing from the list, then there's no way the p box could be 1-to-1. In other words, for a p box to be 1-to-1, all the numbers from 1 up to n better be used in the list specifying the p box. It's okay to have repeats, but every integer from 1 up to n has to be used in order for the p box to be 1-to-1. And if there's any repeated values in the list, then the p box cannot be onto. In other words, for the p box to be onto, every integer in the list has to be unique. We cannot have any repeats. That's the condition to be onto. So just to take a little example here, let's take the p box from b4 to b6 specified by this list. Notice the list has 6 values. That's because we're mapping to b6. Also notice that each integer in the list is between 1 and 4. That's because 4 is the number of input bits. We notice that in this list, the 2 is repeated. So that means this p box cannot be onto. Also, notice that every number from 1 up to 4 has been used. Yes, we have repeats, but that's okay. And that means this p box is 1-to-1. In the bottom example here, we have a p box from b6 to b4. It has 4 elements in the list. That's because we're mapping to b4. And every element of the list is between 1 and 6. We see that the number 6 is missing from this list, though, and that tells us right away that this p box cannot be 1-to-1. Also notice this list has no repeats, so that means this p box is onto. All right, so we have a little bit of intuition there of looking at a p box list, whether it's 1-to-1 or onto. So now we're going to take a look at the p boxes in the data encryption standard, which is abbreviated DES or DES. DES is a 64-bit block cipher, and it uses a 56-bit key. And in its design, DES uses several p boxes in its implementation, and we can take a look at them on this web page here. So in this video, we're actually not going to talk about the DES encryption algorithm, but we can still look at the p boxes that are used in its design just to get some flavor and idea of how p boxes look in real-world cryptography. So the first p box that's used in DES is the initial permutation, and it's denoted by IP. And it's a mapping from B64 to B64. So both the input and output bits are 64 bits there. And here's the list that specifies it. It's to interpret the list, we read it from top to bottom and left to right. The only reason it's written like that is just because it'd be awkward to list it horizontally because it'd be so long. And here's the arrow diagram for that. So the arrow diagram is maybe not as useful as the table, but the arrow diagram does give us a nice visualization of how the permutation spreads out all of the bits in a very uniform way. And opposite to the initial permutation is the final permutation, which is denoted by IP inverse. And that's actually just the inverse of that initial permutation. So this goes from B64 to B64. Both IP and IP inverse are bijections. If we look at this list, we see that every integer between 1 and 64 is used once and only once. So sigma there is a bijection, and therefore the associated P box is also a bijection. The design of DES comes from a Feistel block cipher. And that means it has a Feistel function. Every Feistel block cipher has a Feistel function. And the Feistel function for DES, we'll call it F, it involves the 8 S boxes, S1 up to S8, which we won't talk about in this video. And it also involves 2 P boxes denoted by E and P. So the P box E is called the expansion function for good reason, because it takes a smaller bit sequence, a 32-bit sequence, and increases up to a 48-bit sequence. So necessarily here we have some input nodes which have more than one arrow coming out of it. We can see that in our picture here. And there's our table E there. So E is going to have 48 entries in it, and each entry is between 1 and 32. And necessarily we're going to have some duplicates in there. Also in the Feistel function of DES is used another function just called P, called the permutation function. And it's a bijection. It goes from B32 to B32. And there's the table and the arrow diagram for it. Now, within the key schedule algorithm of DES, which is how we take a key and then produce 16 other keys from it, within that algorithm is used 2 P boxes called PC1 and PC2. PC1 is called permuted choice 1. It goes from B64 to B56. Notice how every 8-bit is ignored. And this is why really the algorithm is called a 56-bit key algorithm, because we're taking in, although we're taking in a 64-bit key technically, notice that every 8th bit is ignored here. So in reality, it's only a 56-bit key. That 8th bit is there for a parity check or something. So this is another example of a P box used in DES in the key schedule algorithm this time. And within that key schedule algorithm, there's also another P box called PC2, which goes from B56 to B48. And this is the P box that gives us the output of this P box, the 48-bit output of this P box, are the round keys for each of the 16 rounds. So this list specifying this P box has 48 entries, and each entry is between 1 and 56. And since we're going from a larger bit space to a smaller bit space, necessarily at least 8 bits of information are ignored, because that's the difference between 48 and 56. Now let's think about how we can code a P box. The very first thing we're going to need to do is just to find a function which can grab a specified bit. So let's say we have some integer x, an n-bit integer. So in other words, it's between 0 and 2 to the n minus 1. And let's say we take some index from 1 up to n. We know that x can be represented as a bit sequence, b1 up to bn. And if we're given an index I from 1 up to n, we want a function, code up a function, which gives us the value of bi. So we can achieve that through this little function here. How do we grab that bit? Well, we first do n minus I, and then we right shift x over by that much. And that puts the bit of interest in the least significant spot. And then to grab it, we do an AND with 1. And that will mask off all the bits that are not significant. And it'll just grab the least significant bit. And that'll be the bit we're looking for. Now, using this idea of how to grab a bit, we can write a P box in general. So we're going to imagine we have a list of integers given to us. Let's write that as capital P. That'll be a parameter for our function. It'll have a certain length to it. We'll call that M, although that doesn't matter for our code. N is the number of input bits, and we really need to specify N as a parameter of the function, because if we're just given the list of integers P, we actually cannot know for certainty what N is. So we need to be given that. And the way we're going to proceed is the value of Y, which we initialize to be 0, is going to be our output. It'll be an m-bit integer. And we're going to cycle through the elements of P. Since there's m elements of P, there's going to be m cycles through this for loop. And what do we do on each cycle of that for loop? Well, we first shift Y over by 1, so we don't damage any of the information on Y, and that leaves its least significant bit open as a 0. And then we append onto Y using the XOR the correct bit value of X, depending on whatever I is from the list P. And we use our previous function that we just wrote there. So notice that each time we cycle through the for loop there, we shift Y over by 1, and then we glue on to the end of Y on the least significant bit, the appropriate bit value of X. And then after that's over, the value of Y will be constructed as an m-bit integer, and every bit of Y came from a certain bit value from X, right? And this is the meaning of the P box. Now the thing is, get bit was just one line of code, so let's just write that directly in. And here we go. This is the code that we're looking for to implement a P box. So any of those P boxes that we saw in DES there can be implemented with this code here. And why don't we try that? Why don't we implement the initial permutation of DES just to see how that works? The very first thing is in our code, we're going to have to make a variable IP, what do we call it, which holds the list which defines this P box. Here's an example from a textbook of the DES algorithm showing all the intermediate values during an actual encryption. Let's just focus on a small part of this. It looks like they made up a random plaintext. It's 1, 2, 3, 4, 5, 6, A, B, C, D, 1, 3, 2, 5, 3, 6. That's just a random value they made up. And then they traced all the intermediate values that DES produces on its journey to getting a final encrypted ciphertext. And for us, let's just look at the very first part that's highlighted there. We take our plaintext, which was that sequence of hex values that I just read. Notice that it's 64 bits, right? Because the number of hex characters there is 16, and each hex character is 4 bits. 16 times 4 is 64 bits. And DES is a 64-bit block cipher. The DES algorithm, the very first thing we do is we throw that plaintext into the initial permutation. And that produces another 64-bit value. And it looks like they're telling us here that after the initial permutation, that plaintext should be sent to this number 14A7D6, etc. Let's verify that in code just to make sure everything's working properly. So here's the code we can use for that. We have our P box code from before, and then we define our IP list, which defines that P box. And let's take X, our input value, to be the hex integer that corresponds to those sequences of hex characters. And the value of Y there is the output of the P box when I feed X into it. Notice I put 64 in as one of the parameters to the P box because that's the number of input bits. And then we're going to print off the hex value of Y. And what we hope for is that we get that 14A7D6 number that we saw. So let's type this in and see if we can make it work. All right, let's open an empty file and code this out and see how it goes. The very first thing we need to do is to define the pbox function. For that, let's take n to be the number of input bits. Capital P is going to be a list of integers of length m. And the integers in P are all going to be between 1 and n. The input x is going to be an n-bit integer, and the output value y will be m bits. And how do we define our P box, which takes in the 3 parameters x, p, and n? Well, we initialize our variable y to be 0, and we return that at the end. That's going to be our output. It'll be m bits. Notice that we cycle through the elements of P, the integers in P. We do that on the line for I in P. And since there's m integers in P, when we go through that for loop, it'll happen m times. And what do we do on each cycle of that for loop? We take y and we shift all the bits over to the left by 1. And what that does, it introduces a 0 in the least significant spot, and it also keeps all the current bit values of y. None of the bit values of y are damaged. And then when we XOR it on the new bit, it goes into the least significant spot, and it doesn't affect any of the previous bits that were set in the loop. And what we do is we access the ith bit of x, right? And we do that not by shifting x to the right by I, but by shifting x to the right by n minus I. And what that does, it places that bit bi in the least significant spot. And then when we AND it with 1, that grabs it. And that's the value of the bit that we're looking for of x. It's either 0 or 1. And then we glue it on the end of y. And then we just repeat that process. And after we cycle through all the elements of P, y has been constructed, and that value is returned, and that's the value of the P box. Now, just to test this, to see if everything's working, why don't we implement the initial permutation of DES? So the initial permutation will write IP for the list that defines it. There's 64 integers here. They're all between 1 and 64. Remember, IP is a bijection between B64 to B64. And we take that X value as our input, just some random cipher, just some random plain text. And it's 1, 2, 3, 4, 5, 6, A, B, C, D, 1, 3, 2, 5, 3, 6. That's a hex value. We use our code to convert it to an integer. And then we feed that value of X into the P box. The other parameter is IP and a 64 because IP has 64 input bits. And the Y value that comes from that is the value of the P box. And let's just check that we're getting the proper value. Remember, we're supposed to get this value 14A7. So let's define that to be Z. And let's just do a little if statement to see if Y really did turn out to be Z. And if it did, then it works. And when we run this in Python, we see that, yes, it works. That's great. And that brings us to the end of this video. Thanks for watching.